Hello and welcome to all of my dear student of third year BSc class. In previous lecture we have studied about SOP, that is sum of product, and standard SOP form, that is standard sum of product form, and how we can convert simple SOP into standard SOP. Now in this lecture we are going to see the second part of this article, that is the procedural steps to convert product of sum expression into standard product of or standard POS form. Okay. In previous lecture we studied the procedural steps to convert SOP expression into standard SOP expression, and now in this lecture we are going to see the procedural step to convert POS expression into standard POS form. First of all, what is POS? What is POS? POS is nothing but product of sum. Product of sum. When two or more sum terms means A plus B bar. This is the sum term. This is the sum of A and B bar input. Or we consider another steps, A plus B, A bar plus B plus C bar. This is also the sum term because this is the sum of three inputs, A bar, B and C. Now here the product of this sum term and this sum term is called POS form or POS expression. Okay, have you got it? POS expression means the product or when two or more steps are multiplied or product, then resulting expression like this is known as POS, that is product of sum. Here this is the sum term and this is another sum term, and product of these two sum terms is nothing but POS or product of sum. Okay, we can see another example. Y is equal to A plus B plus C. This is the sum term. This is the sum of three input term. Then another term, suppose vector A bar plus B, or consider another term vector bar A plus bar B, or instead of this we can take any. Now see here, this is the sum term of three inputs. This is the sum of two inputs, A bar plus B. This is also sum of two inputs, A bar plus C bar. C bar. And now when we take the product of these three term, we have the expression y is equal to this into this into this. This is also another example. Suppose this is expression number 1. This is expression number 2. We can consider one more example. Suppose A plus B is the sum term, which is the sum of two inputs A and B. Consider another term, vector A bar. This is bar A plus B. Consider another term, B plus A bar. This is another term, or we can take complements of also. So this expression y is the product of these three terms, sum term, first, second and third. These 1, 2, 3, these are the sum term, and product of first term with second and third is the expression, and all these expressions are known as product of sum or POS form. Okay. See here, now when we observe these three equations, in all these equations are POS form, and in this POS form, or in all, when we look toward these three equations, then it is found that a single bar, only single bar here, only single, there is a single bar, only single bar over a variable. But a single bar cannot be extended over more than one variable. That is not like this, b plus a bar, not like this. This is the bar extended over these two variables, or a, b, c. When we take like this, then this is the bar extended over three variables. This is the bar extended over two variables. But this is not the case here. Here it is found that only one variable on which there is a bar. Okay. Now POS expression, POS form expression have sum like this sum or this sum, and when we take the product of these two sum term, we will get the POS form. Okay. It must be noted that all these equations are in POS form but not standard form. What I say, all these three equations are POS form but not standard POS. Okay. Only this equation 3 is standard POS expression or standard POS expression, because this equation, or in this standard POS equation, each term include all the literals or all the inputs in complemented or uncomplemented form. Here equation 3 is having two literals or two inputs, and every term is having two same inputs, though either in complemented form, these are the complemented form, and this is the uncomplemented form. Though it may be complemented but uncomplemented, but every term should have contain all the literals. Here two literals or two inputs and b, and every term there is a two literals either in complemented form or in uncomplemented form. So only equation 3 is standard POS, but first term of equation 1, okay, and second and third term of equation 2 missing something. Here only two literals and here three literals. If this first term missing C or C bar, now this term missing C or C bar, and this term missing B or B bar. So these, due to missing of these literals, these two equations are not standard POS form. Okay. Now here again we have to see in terms of max term and min term. Here equation 1 and 2. Equation 1 and 2 given, the expression given by equation 1 and 2 are not standard form or not standard POS form because first term of equation 1 missing C or C bar, and second and third term missing, the second and third term of equation 2 missing C or C bar and B or B bar respectively. Only this equation 3 is standard POS because there are two literals or there are two inputs A and B, and these three sum term includes both the literals, though in complemented or uncomplemented form. So equation 3 is called max term. Equation 3 is called max term, or simply M. Okay. Now, in order to understand this, or how we can convert POS form into standard POS form, there is a procedural steps. For that purpose, consider a logical expression like this. Consider a logical expression y is equal to a plus b into another term a plus c into another term b plus c bar. Okay, this is the expression. This is POS expression, that is this expression having three terms, multiplied terms, or this expression is the product of three sum term, this one and this one. So this is POS form, product of sum form. Okay. Now we have to convert this product of sum expression into standard product of sum. Okay. For that purpose, what we have to do? In this expression, there are three variables or three literals, A, B and C. Now, these three variables either in complemented form or uncomplemented form. But if we look toward this expression, then it is found that the first term of this expression missing C or C bar. Okay. Second term missing B or B bar. And third term missing A or A bar. Okay. So this equation is not standard POS. And when we want to convert this simple POS into standard POS, what we have to do? We have to multiply, we have to add C or C bar in first term, B or B bar in second term, and A or A bar in third term. So we have y is equal to A plus B into plus C bar. Okay. We added this. Okay. Because C into C bar is equal to 0. What is, suppose C is logically 1 and C its complex conjugate is 0. 1 into 0 is 0. So this is it. Okay. Now second term, A plus C plus we have to add B into B bar. Again remember that B into B bar is 0. Why? Because when B is logically high, its complex conjugate is low. So 1 into 0, 0. Now third term, B plus C plus A into A bar. Again, A into A bar is 0. B into B bar like this. When A is logically high, then its complex conjugate A bar is logically low. Again 1 into 0, 0. Okay. So from this, A into A bar is equal to B into B bar, or B into B bar is equal to C into C bar is equal to 0. Okay. And when we take 0, C dot C is equal to 0, B dot B is equal to 0, A dot A is equal to 0, sorry, C dot C bar is equal to 0, B dot B bar is equal to 0, and A dot A bar is equal to 0. When we put this term, then there will be no any effect, or there will be no any change in this expression. Okay. Now, what we have to do? For simplify this equation, we can simplify this like A another term plus B plus next term. Okay, one by one. We can see one by one. A plus B plus C into C bar. Solve this term. What is the result? A plus B plus C. Okay, A plus B bar. Okay. Now, second term, A plus B into C bar. When we solve this term, we will get this. Okay. Similarly, next term, A plus C plus B into B bar. Solve this, we will get A plus C plus B. And another term, A plus C plus B bar. Okay. Now third term, B plus C bar plus A dot A bar. Now simplify this term, we will get B plus C bar plus A, first term, into B plus C bar plus A bar. Okay, these are the, when we substitute these value, that means this one, this one, this one in this equation, instead of this bracket, this bracket, this bracket, we have y is equal to A plus B plus C into A plus B plus C bar into A plus C plus B into A plus C plus B bar into B plus C bar plus A into B plus C bar plus A bar. Okay, we just rearranging sequentially. So here A plus B plus C as it is, into here A plus B bar, sorry, B plus C bar as it is, here A plus B plus C, here again into A dot B bar, sorry, A plus B bar plus C, and here A plus B plus C bar, last term A bar plus B plus C bar. We just make the sequence. Now, when we observe this equation, then this is here, this term A plus B bar, A plus B plus C is double. So this is redundant term, and this term and this term is again double. So this is also redundant term. Now when we eliminate these two redundant term, that means what we have to do? Instead of two, we have to consider only one term. So next equation is like this: y is equal to A plus B plus C. This is the redundant term first. Then second term, A plus B plus C bar. Okay. Instead of this two term only, we consider only single term. Instead of this term, we consider only one term. So A plus B bar plus C into A plus B, sorry, A bar plus B plus C bar. We get this equation, and this equation, then we look toward this equation. Obviously, every sum terms have all three literals A, B and C either in complemented form or either in uncomplemented form. So this equation is standard POS expression or standard POS form of this expression. This is POS form but not standard POS form, and when we follow this procedure we can convert this POS form into standard POS form. Okay. Now we are going to see the next point of this chapter, which is also interesting and important for in all respects and for exam point of view. Next one, reduction of Boolean expression. Reduction of Boolean expression using Karnaugh, K-R-N-A-U-G-H, Karnaugh map, or simply K-map. Okay, K-map method. Okay, here we are going to see the new point, interesting point, very important point in all respect, to reduce the Boolean expression using Karnaugh map or K-map. Okay, students, we are familiar with Boolean laws and De Morgan's theorems, which is used to simplify Boolean expression. We already studied this in TYBSc electronic first. Okay, what I say? So I told you that we are very familiar with Boolean laws. And Boolean laws and De Morgan's theorem. By using these Boolean laws and De Morgan's theorem, we can simplify the Boolean expression. Okay, but this simplification process is very tedious and time consuming. What I say, I am again going to repeat. We are familiar with Boolean laws and De Morgan's theorems, which is used to simplify Boolean expression. But this simplification process is very tedious one and time consuming process. Okay, the K-map, that is Karnaugh map, provides a systematic method. K-map provides systematic method. To reduce or not reduce, K-map provides systematic method for simplification of this Boolean expression to their minimum form. That is small m. Okay, this is very interesting one and this is very important. So before studying in details the K-map, I would like to tell you that once again So you can't confuse. Okay. I am again going to repeat these 2-3 lines once again. We are familiar with Boolean laws and De Morgan's theorem, which is used to simplify Boolean expression. But this simplification process is very tedious one, very time consuming. So the K-map or Karnaugh map provides a systematic method for simplification of this Boolean expression to their minimum form. Okay. Now, what is K-map? See here. What is K-map or what is Karnaugh map? The basis of K-map, is graphical representation. Graphic representation. The basis of K-map is graphical representation of mean terms, minimum terms or minimum terms, that is small m, or max term, that is capital M, in a chart or table, and this is called K-map. Okay, have you got it? What is K-map? The basis of K-map is a graphical representation of minimum term or maximum term in a chart or a table is nothing but K-map. Okay. We studied the truth table at TYBSc. Suppose for OR gate of 2 input and 1 output, the truth table is A, B, 1, because Boolean expression is for OR gate is A plus B. By using this Boolean expression, we can prepare the truth table like this. When A is logically low and B is logically low, output is low. When A is logically high and B is logically low, then output is high because A plus B. When A is logically low and B is logically high, then output is high. And when both A and B are logically A or B is logically high, then output or both are, then output is high. Okay, so what is the condition? Either A or B or both. When A or B or both are logically high, then our output is high, and hence the name OR gate. And this is the truth table for OR gate. We also studied the truth table for AND gate in previous lecture. Suppose this is the AND gate, and this AND gate is having 2 input A and B and having single output Y. What is the Boolean expression? Y is equal to A dot B or A into B. So this is the multiplier gate. So when A and B, A is logically low and B is logically low, then output is low because A dot B. When A is logically high and B is logically low, then output A into 1 into 0, also 0. When A is logically low and B is logically high, then output is also logically low. When A and B are logically high, A and B is logical, then output is high, and here's the name. And A and B is logically high, then output is logically high. So this is the, and this is the truth table of AND gate. Okay. Like this, there are NOT gate, then combination of AND and not is nothing but NAND gate, and combination of not and or we have NOR gate. This is the hybrid gate. NOR gate, NAND gate, XOR gate. This is the hybrid gate. But OR gate, AND gate and NOT gate, these are the basic logic gate. When we make the combination of NOT and AND, we will get NAND. When we take the combination of NOT and OR, we will have NOR. So these are the NOR, NAND, XOR. These are the combination of basic logic gate, and hence these are the hybrid gates. And we studied the truth table of all the simple and hybrid gate, as well as we also studied De Morgan's theorem in TYBSc, at TYBSc in electronic first paper. Okay. Now, as I told you that the basis of KMF is a graphical representation of min or max term in a chart or table. This is nothing but KMF. Okay. Second thing, the KMap is similar to this truth table. When we plot where we represent the KMap is similarly looking like this truth table, or in simple word we can say that KMap is similar to truth table because it contains all the possible values of inputs input variable and resulting output for each value. Okay, what I say? The KMap is similar to truth table because it contains all the possible values of input variable and resulting output for each value. Okay. Third important point regarding KMap. KMap is an array of cell. Array of cell, that means similar type of data. KMap is an array. KMap is an array in which each cell represents binary values. Every cell contains binary value, either 1 or 0, and hence this is an array. KMap is an array of cell in which each cell represents binary value of input variables. Okay. Another important point regarding KMap is like this. The number of cells in KMap is equal to total number of possible combination of input variables. Suppose KMap for two variables. KMap for two variables is equal to total number of possible combination of input variables. Suppose two variables, so KMap has 2 raised to 2 is equal to 4 cell. 3 variables. 3. If there are 3 variables, then 2 raised to 3 is 8. So KMap have 8 cells. And when KMap for 4 variables, this is for 2 variables, this is for 3 variables, and this is for 4 variables. Then 2 raised to 4 is equal to 16. Okay. Here it is very interesting one, the number of cells of KMap. These are the KMap cell of KMap for 2 variables. When 3 variables, here 2 variables A and A bar, B and B bar. Okay. So this is the here A and here B. This is the KMap for 2 variables. Now there are 4 cells because 2 variables. 2 raised to 2 is equal to 4. When we consider 3, then we have 8 cells like this. This is the variables. 3 variables. So there are 8 cells, or like this. Like this. Okay. And there are 8 cells. 1, M0, M1, M2, M3, M4, M5, M6, M8, or M0, M1, M4, M3, sorry, M3 and M2, M4, M5, M7 and M6. These are the 8 cells here also. Okay, in this way. And when there is a 4 variable, then obviously cells, M0, M1, M3, M2, M4, M5, M7, M6, then M8, M9, M11, M10, then M12, M13, M15 and M14. These are the 16 cells. This is the K-map for 4 variables, that is A, B and C, D. And this is A, B and C. This is A, B and C. There are 3 variables. This or this having 3 variables. This or this K-map is for 3 variables. This is for 4 variables. Okay, like this. Now, every cell contain either 0 or 1. 0 or 1. And this product term or different figures shows the structure of K-map for 2 variables, for 3 variables, for 4 variables, and with 0s and 1 are written on the top side or boxes of the boxes represent the values of corresponding variable. The product term is assigned to that cell. And how product term is assigned to that cell? That is nothing but structure for 2 variables, K-map structure for 2 variables, K-map structure for 3 variables and K-map structures for 4 variables are different and interesting, but lack of time it is not possible to cover all these things in this lecture. So in next lecture we will see the structure of K-map for 2 variables, or K-map structure for 3 variables and K-map structure for 4 variables. Till then we shall stop here. Have a good day. Thank you.